You guys, 4.3, logarithmic functions. Okay, so I think you've probably seen logarithms before, and a lot of times when people first see them, they seem a little tricky. What I want you to realize is a logarithm is just another way of writing an exponential. Okay, so here's the definition. For all real numbers y and positive numbers a and x, okay, so my bases are going to be positive, and right here what I call the argument of the logarithm, and what I have over here is going to be positive. Y is equal to log base a of x. It means the exact same thing as a to the y equals x, okay? So usually the way I like to think about this is right here, this is log form, and right here, this is exponential form. And a lot of times we want to convert between these. Especially in this section, we'll be converting from log form to exponential form a lot. Okay? But sometimes we want to do the other way. So let me show you how this works. Suppose I have this equation, x equals log base 3 of 9. Okay? So the question is, what's x? Well, most graphing calculators won't do a log base 3. Some will, some won't. But what I have to realize is, well, hey, this is in logarithmic form. I'm just going to go ahead and write this thing in exponential form, okay? So the base here is the same as the base here. So I know this is 3 raised to the x, okay, is equal to 9. That's what you want to get used to when you see an equation like that. And we know how to solve this, right? Because we know that 3 to the x is equal to 3 to the third, getting the same base like we did in the last section. And from there, if the bases match, we know the exponents, of course, have to match. Let's try this one. So now notice the x, what we're looking for is in a different spot. It's in the argument of the log. The log is, it's like a function, okay? So x is sort of, it's like if we had f of 2 or something like that. So same thing I'm going to do. I'm going to write this thing in exponential form. And that would tell me that the base to the third is equal to x. Well, that's actually pretty easy. That's just x equal to 64. Okay, so that's how to do it if the x is in that position. What about here? Log base x of 16 equals negative 2. Okay, now it's in the base. So there's one thing I want to point out before we start. This x, as we said here, the base right here, has to be positive. So here, it should be strictly positive. Okay, that's what we should get. Let's do the same thing. So x to the negative 2 is equal to 16. Okay, so now there's options on how we can do this. Okay. One thing I could do is I could raise both sides to the negative 1/2. Why did I choose negative 1/2? Well, because I know negative 2 times negative 1/2 is just x. Okay. Now here's the thing. If I'm raising it to the negative 1/2, technically that's like I'm taking a square root, right? Just in a denominator. Normally we put plus or minus. Here I don't put plus or minus because our answers are strictly positive. So for that reason, I don't have to worry about that. So this is 1 over 16 to the positive 1/2. That, of course, is 1 over root 16, or 1/4. And it's not plus or minus 1/4, it's just positive 1/4 because of our restrictions above. D, log base 1/3 of x plus 6 equals negative 2. Same idea. Take your base, raise it to this power over here, and that's equal to the argument. Well, this I know is the same as the reciprocal to the second power, and this is a lot nicer now. X is going to be equal to 3. Okay. Last one, E right here. I want to look at this. So we'll do the same thing. We'll say, okay, the base to whatever the other side is on the other side of the equation, x to the 3x minus 15 is equal to the argument of the log. So when you look at this, this might look a little tricky because you're like, oh, I got an x for the base, and I have another x in the exponent. How am I supposed to solve that? Here's the thing, okay? anything to the 0 power is equal to 1, right? We know that. No matter what the base is, anything to the 0 power is 1. So if x to the 3x minus 15 equals 1, well, that means that this to be equal to 1 must be 0, right? This must be 0. So just 3x minus 15 has to be 0. If that exponent is 0, I know this will be true, no matter what x is. So 3x is equal to 15. X is equal to 15 over 3, or x equal to 5. Okay. All right. So what I want to talk about now is if you have a logarithmic expression rather than an equation. So suppose you have this. Someone just says, hey, log base 2 of 4, right? We say base 2 of 4. 2 is the base, 4 is the argument, okay? And they say, well, what is that, okay? Well, if it's base 10, you can do it in your calculator. What this is saying, just think about how we look at this. This is saying 2 to the what power is equal to 4. Okay. Well, of course, the answer to that is 2. So whenever you see an expression, I would encourage you to do it like that. Take your base and say, oh, what power is it raised to get the argument? That's the same thing we were doing with the equations. I just wanted to make sure it was very clear. Okay. So let's see what we got here. Log function, base A, okay? So what I'm going to do is I'm going to graph 2 of these things. First, I'm going to do an exponential function, okay? We know what 2 to the x looks like. We know 2 to the x goes like this. We know we have the point -1, comma 1/2, 0, 1. This is from the last section, and 1, comma 2. Okay, so we're right here. And over here, for log base 2 of x, here's how we're going to do it. I'm going to try to do the same thing, and I'm going to pick just some sort of convenient values. So I'm first going to let x be 1. If that's true, then y is log base 2 of 1. Okay? There's my argument. Well, if I rewrite this in exponential form, this is saying 2 to what power is equal to 1, and that what power has to be 0. So I have 1, comma 0. Okay? So that's right here, 1, comma 0. Next value I'm going to choose is I'm going to choose 2. Log base 2 of 2. In exponential form, that says 2 to what equals 2. Of course, that what is 1 right there. So I have the point 2, comma 1. 2, comma 1. Are you noticing anything? Over here I had 1, 2. Here I have 2, 1. Over here I had 0, 1. Here I have 1, 0. Interesting. Finally, what if I go ahead and I choose a value of 1/2 for x? Log base 1/2, log base 2, okay, of 1/2 means 2 to the what is equal to 1/2. Well, that what is -1. So I have the point 1/2, comma -1. 1/2, comma -1. Here's what I want you to notice. That also switched. These things are inverse functions. You can keep looking to verify, or you can even check what f of g of x or f of g of x is if one of these are called g. But here's the thing I want you to notice. Their bases are the same. If these weren't the same, they wouldn't be inverse functions. And what happens is as you get closer and closer, you never quite reach that y-axis. And this keeps kind of going here. Oh, okay, well, if we never reach it, but we get closer and closer, I guess that would be a vertical asymptote. Well, hey, over here we had a horizontal asymptote of y equals 0. Over here, the vertical asymptote is x equals 0. Remember we said in inverse functions in 4.1, the asymptotes switch, the horizontal and the vertical. So this makes sense, okay? So that is what we're noticing here. Notice the domain and range will change. We'll look at those in the next video.